Good morning, folks. Advanced Higher Chemistry, a multiple choice walk through. Slightly contentious today. As you can see by the date, no, that is not a typo. There was a paper for 2021. Never officially released, although I believe, sadly, it was leaked. So I'm reliably informed. So let's have a look at my version of the answers. As usual, this is the acoustic uncut version where I do have the answers, but I haven't looked at them yet. So you get to catch me making all my mistakes, which hopefully might stop you making some similar mistakes. Number 1. According to the Aufbau principle, electrons fill atomic orbitals of potassium. Potassium is at number 19. So it's, this is just checking it out. So 1s, 2s, 2, 3p, 3s, 3p, 4s before 3d. So that's C. 2. Which of the following is not a possible? I'm notorious for missing the nots. Not a possible quantum number for an outer electron in oxygen in its ground state. So we're talking outer electrons, and it's got to be oxygen in its ground state, so no promoted electrons. L equals 0. So oxygen, by the way, will be 8 electrons, so 1s2, 2s2, 2p, I can't count this time in the morning, 2p4. So outer electrons, those are the outers, so that's a nope, it's not that one. L equals 1. Yeah, it could be. Oh, which is not. Handily did it again. What a spanner I am. That's A. The number of unpaired electrons in a chromium atom in its ground state. Chromium atom. So no ions. Chromium is number 24. So we're talking 4s2, 3d. Let's count along. 1, 2, 3, 4. 3d, 4. So these electrons fill up the d orbitals. 1, 2, 3, 4. Number of unpaired electrons is simply 4. There you go, nice and easy because they haven't doubled up yet. Number 4, get on camera, hey, pretend to be professional. Number 4. Oh, by the way, can I interrupt this broadcast for a public service announcement? If you are watching these videos on a mobile platform like your iPhone, if you're daft enough to pay for Apple money, or an Android phone, or any other mobile platform, you realize you can get an ad-free YouTube experience. Just install Firefox, pop an ad blocker extension into your Firefox, and then watch YouTube as a Firefox webpage, and ta-da! No more adverts, ever. Thank me later. Number 4. What's going on here? We've got X, Y, and Z. We've got Ka, which is the dissociation constant for acids, for weak acids. Negative 11, negative 10, negative 5. So that's the strongest acid, and that's the weakest acid. Does that help us? X is less basic than Y. They're asking about basicity. That's tricky. Let's go for the acidity ones first of all. X is more acidic than Z. No. Y is less acidic than X. No. Which means, of course, we're going to be going off one of more of these. Now, Z is a stronger acid. Z is not mentioned. X, Y and Z. Oh no, Y and Z are more mentioned though. Y is more basic than Z. I'm inclined to go with that on the basis that Z is the most acidic. X is less basic than Y. X is less acid than Y, because the number's smaller here. I'm going to go with C. Let's see if I'm wrong at the end. At 1400 Kelvin, we have got, okay. Oh, okay, this is just calculating delta G. Delta G is defined, interestingly, with a circle. Because I thought that was standard conditions. Anyway, let's not argue over that, and we're definitely not standard temperature here. Anyway, delta G is known as the sum of the delta G of all the products minus delta G of all the reactants. So it's calculator time. I may pause the video because there's no point in watching me do boring calculations. Scratch that, just unpause the video again because this is a more interesting question than it looks at first glance. Here's the overall reaction. And you're sort of building up the reaction from these two. So this is more like a Hess's law one. It's interesting. If you notice, of course, we're involving 2 carbons and 2 carbon monoxides and 2 zincs and 2 zinc oxides. And that's not what's happening here. So it might not be that at all. It might be more of a Hess's law version, which is a very sneaky way to hide this question. So if I was to assemble this, Avenger style, if I was to assemble this equation from these two, I would say we have a carbon on the left, so we're going to take half of that value. We also need a zinc, but we need the zinc on the right. And there's 2 zincs here for this number here. So I think what we'll do is we'll flip that equation and we'll half it. So we'll add, instead of negative 340, we'll add half of positive 340. This will be interesting to see if I'm wrong. So we need 475 times a half, and we need to add to that 340. We're getting negative 67.5, which is an answer, so that's a good start. Let's see if I'm wrong at the end. Number 2, enthalpy of formation. You have to be making 1 mole of the compound, so that is scratched straight away. So is that. You have to make 1 mole of the compound from its elements in their normal states at room temperature. Enthalpy of formation of a compound. Why am I getting in my brain 2 correct answers on this one? That's an interesting one. Have I done anything wrong? You have to assemble it from its elements, and the elements and the products have to be their standard states at room temperature. Magnesium solid, oxygen gas, magnesium oxide, sodium bromide. I have to come back to this one. Okay, no problem. I'll put a little reminder at the end of the paper to come back to question 6. Just in case I forget, let me pop it at the very end. Question 6, there we go. Okay, let's move on. Don't burn time in your exam, guys. Just as a general exam technique, if you're puzzled, come back to it later. Number 7, is it possible I have misread the question? Entirely possible. Kinetic data for the reaction between bromate and bromide ions is shown below in the presence of hydrogen ions. Okay. Which table shows the order of reaction for each reactant? Right, let's have a look. So from experiment 1 to 2, we have doubled the bromate and we have doubled the rate. So it's a first order with respect to bromate, which is good because we can scrub that answer. What about bromide? If we compare these 2 reactions, we have doubled bromide and not touched anything else. What have we done there? We've doubled it again, it being the reaction rate. We've doubled the reaction rate, so it's first order with respect to bromide as well, which means we can scratch that one, which just leaves us with hydrogen ions. So if we compare this reaction with this reaction, then everything's the same except for the hydrogen ion concentration. And note that's -4, guys, and that's -3. So that's actually multiplied by 4, which is times 2 to the power of 2, and this is times 2 to the power of 1, which means this is a second order reaction. So the answer is B. How are we doing? Let's move on. Question 8. Can we fit question 8 on the page? Just about. Yes, we can. Which of the following graphs would be obtained for a reaction that is 0 order with respect to X? Now, we're showing rate against concentration of X. In other words, if you change the concentration of X, it will have no effect on the rate. That is the definition of a zero order, which takes us to that one. Number 9. For the reaction 2P plus 2Q makes that doesn't matter. Actually, the rate equation is this, though. We're seeing P to the power of 2, Q to the power of 1. That means there are 2 molecules of P and 1 molecule of Q in the rate determining step, which is the slowest step, which is not that one. We could ignore the fast step, by the way, because that doesn't affect the rate. 2 P's and 1 Q. I'm going to go with that one. It's not that one, because although we see 2 P's and 1 Q, that's the fast step. Yeah, that's nice and easy. Number 10. For the reaction, we got 2-bromopropane plus it's a nucleophilic substitution. Which line in the table is correct? Okay, so OH is a nucleophile because it's a negative charge. Can also have an unpaired pair of electrons, but it doesn't in this case, it's just negative charge. So OH is a nucleophile, which means we can chuck out these two. And the structure of this, that is a secondary alcohol, because there is no methyl group on that third carbon. It's just that. So secondary alcohol, which is answer A. This seems to be a relative, famous last words, this seems to be a relative breeze. So far I'm only stumped by that enthalpy of formation. That's really annoying me. Let my subconscious chew over it and see if it comes up with any inspiration. Which of the following reactions involves homolytic fission? Homolytic fission is where you split a bond equally. And definitely not that one. Basically, you want a non-polar bond. So the only non-polar bond here is in a bromine molecule. So it's going to be B. That's heterolytic fission. That's nucleophilic substitution. There's no bonds broken there anyway. And that is electrophilic substitution because it involves benzene. Just for Fatima, here we have a happy benzene. Which of the following has the fewest sigma bonds? Sigma bonds are normal, whatever that means, carbon-carbon single bonds. So which is the fewest sigma? Oh, interesting. All involve 6 carbons. I was thinking, can we chip off the carbons? No, we can't, but I'll tell you what my mind has jumped to as a shortcut here. Sigma bonds also involve C to H, not just C to C, which means if we can find the molecule with the fewest CH bonds, we'll have the fewest sigma bonds. I'm going to jump straight to this one here, hex 1-ine. 1, 2, 3, 4, 5. Oops, sorry, that's on there. There are no CHs on there. I would come back and check this at the end of the exam if it was my exam, but I'm going to go with the answer C for speed for you good people. I would come back and I would add it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 sigma bonds on that, and I would come back and double check the rest later. Number 13, propyne. 2 alkyne questions right next to each other. Undergoes addition reactions. Assuming the reaction between a propyne and hydrogen chloride follows Markovnikov's rule. Now, I joke in the class with Markovnikov's rule that hydrogens are cliquey. So the hydrogen goes and sticks to the carbon with the most hydrogens already on it. We then go on to look at the real reasons why Markovnikov's rule happens, but that's the mental shortcut that I joke about being easy to remember, which means, in this case, that hydrogen, a choice of going onto these carbons is going to go onto this carbon here. So we'll pop the hydrogen on there, we'll pop the chlorine on there. A possible product could be, I'm just thinking in my head, but you can then, that will go to a double bond, and then you could do the reaction again. However, if you did the reaction twice, you would have 2 chlorines, not just 1 chlorine. I was trying to differentiate between these 2 answers here in my head there, by the way. 2-chloropropane and 2-chloropropene. It wouldn't be that one, because you would, if you added HCl here once, you would create CCC, and then a chlorine on there, double bond on there. And then you'd be able to add another hydrochloric acid onto that once more, which would create the dichloro compound, and that's not what we're seeing. So yeah, I'm going to go with D. Are we still on camera? Yes, we are. Bit late to ask that after you've already done the question, hey? Yes, spanner. Okay, number 14. An ester is formed by condensation reaction between this is an acid chloride. That's unusual. That's a hangover from the old SYS syllabus, if anybody is old enough to remember that other than me. So this is an acid chloride. Instead of a carboxylic acid, we have substituted the chlorine instead of the OH. It just makes the reaction go faster. So what are the products of this reaction? Well, you're going to join these two together and you make hydrochloric acid. So we can chuck out these two. The structure of the ester would look like this. It's going to bond to that center carbon. Let's rearrange it a bit. So you'd end up making that. By the way, there's an oxygen in there. I am truly incompetent. My apologies. So that's the structure of the ester. What does that match up to? CH3, CH2CO. That's the carbon with the double bond because it's bald. It's got no... I feel its pain. It's bald. It's got no hydrogens on it. And then CH... CH3. Yeah, that looks about right. Why is this one wrong? Because the acid carbon... Ah, I see why. Because the bald carbon there is on the side with the two branches, and that's not the case here. Got you. Going to go with C. Secondary amines react with some carbonyl compounds to form unsaturated... This is news to me. This is not part of the course, so problem-solving time. So we've got a secondary amine. So there's my secondary amine. R3, R4. What's happened here? R1, R2. We form this. So this hydrogen has gone bye-bye, and the nitrogen has stuck directly to the carbon. So the hydrogen and the oxygen have said bye-bye, and the nitrogen is now bonded to this carbon, and we've formed a double bond onto there. That's how we get this structure. I don't know about you, but it's early in the morning for me, so I'm tempted to redraw this in the same style as above. Just rotate it around. It's not like the SQA to make your life that little bit more difficult, is it? They've rotated this structure around. Which carbonyl compound would react with CH3, so N, CH3, CH3, NH, to form this. So we can scratch that out of the way. Sorry. Single bond to a carbon. And then it would be double bond to here. There's a C on here. And there's another C on here. Right. So I've just rotated this around structurally, that is. This is where I'm notorious for getting things wrong, by the way, so feel free to shout at the screen if you see me making any mistakes. There's no point, of course. I can't hear you. You could leave a comment, I suppose, if you fancied. You're welcome to. Anyway, back to the question. So we take this compound here and rebuild it in its previous form before it reacted. That would be butanone. I'm going to go with D. That's a tricky problem-solving one, that one, because we've never heard of enamines. That's okay. That's what problem-solving is all about. Number 16, which of the following functional groups is not, read the question, hey, present in warfarin? Carbonyl. Well, I'm seeing a carbonyl, so that's not the answer. Carboxyl. I don't see a carboxyl, so that could be the answer. Hydroxyl. Nope, I'm seeing the OH there. Phenyl. That is a phenyl group. It's a benzene ring as a substituent on another chain, which makes it phenyl. So that is B. Which line on the table is correct for a high-resolution NMR spectrum of ethoxyethane? Number of hydrogen flavors. Well, there are, in fact, only 2 flavors of hydrogen there. There's a CH3, which is attached to CH2, which is attached to the rest of this. And this is a mirror of that. And the second flavor are these ones, which are also identical to each other. So, scratch them. This is next door to 3 hydrogens, and if we use the n+1 rule, where N is the number of hydrogens on the neighbouring carbon, then you'll get a quartet. So that will be split for a quartet. Sorry, these ones will be split into a quartet. And these hydrogens here have a neighbouring 2, which means N plus 1. These will be split into a triplet. So we're talking A. Although NMR spectroscopy is a horrendously complex topic, because it is so complex, not that many people understand it properly, and the questions always tend to be quite straightforward. Hallelujah. Number 18. Which of the following amines is likely to have the lowest boiling point? Oh yeah, classic question. How are you supposed to know? Lowest boiling point means there is no hydrogen bonding involved in this amine, which means you need a tertiary amine. So there can be no hydrogens on the nitrogen, which means we instantly chip straight to D. 19. Ethane can be prepared by adding iodomethane to sodium. So that's iodomethane, that's sodium. When a mixture of iodomethane and iodoethane is used, what's going on here? How have we formed this? Well, presumably, the CH3 attached to the iodine has coupled up with another CH3 which was attached to the iodine, and we form C2H6 instead. So if you're using a mixture of iodomethane and iodoethane, the only alkanes produced are right. So if I join CH3 to CH3, sorry, I'm not explaining this very well. If we have iodomethane and iodoethane, then what you could get is you could join this to itself to make ethane. You could also join this to itself, I suppose, which would make butane. And I suppose you could also mix that with that, which would make propane. So I'm going to go with C. Ethane, propane, butane. Quite a nice problem solving on that one. Which of the following will react with lithium aluminium hydride but not react with Tollens reagent? This is a reducing compound. So which of the following can be reduced but not oxidized? Oops, sorry. Is effectively what they're asking. Well, this one here can be both, will react with Tollens, that's for sure, because you can reduce it back to an alcohol and you can oxidize it to a carboxylic acid. This one here is an ether. That's an aldehyde, this is an ether. That doesn't react with anything, so that's out. We're left with an alcohol and a ketone. Now, the alcohol cannot react, it can be reduced, so that's out. So we're left with the ketone, which indeed can be reduced but cannot be oxidized, which was my original diagnosis. Should have just stuck with that. I was making work for myself there. Life's too short to generate work for yourself. 21. Two substances were analysed and found to have the empirical formula CH3O. From this information, it can be concluded that the substances are isomers of each other. Maybe. Same molecular mass. Actually, maybe not, because they could be doubled. It could be C2H6O2. So that's possibly not true. So I'm going to go with no, that one. Same molecular mass, no, for the same reason. For the same logic. Have the same functional groups? Definitely not. Because it could be any arrangement of... Oh yeah, of course, the same percentage mass. Yes, because it's the same ratio of carbon with respect to all the other elements. 22. Oh, this is an old chestnut of a problem solving. I've seen this over the years so many times. Yeah, it's problem solving because all you do basically is stuff the numbers into here to solve this. Never seen this equation before in our lives. Lambda as some sort of constant energy level to which the electron falls, energy level from which the electron falls. When an electron falls from the 9th energy, so basically N1 in this case is being 2 to the 2nd energy level, and N2 falls from N2's 9. Pop these numbers into here, pop the number for R in as here, and out comes the wavelength. The tricky thing here is this gives you the reciprocal of the wavelength, so you actually get to use the reciprocal button on your calculator. How exciting! And I can't see where the reciprocal button on this calculator is because I'm an old fool. Let me pause the video. There's no point in watching me work this out, so let me pause the video while I put these numbers in and hopefully get the right answer. I found the 1 over button. It's hiding there, x to the -1 on my calculator. I get this answer here, which you may or may not be able to see on the screen there, which is looking like 3.8 to the power of... I don't even need to answer that. There's only one 3.8. I'm going to go with B and hope that I'm not making myself look like a muppet. 23. The low resolution NMR spectrum for an organic compound is shown below. That's not very interesting, NMR. A single spike. That doesn't count, of course. That's your calibration spike for tetramethylsilane. Propane. Oh, definitely not that one. That would have more than one flavour of hydrogen. Oh, of course, it's propanone. It's the only one that's got a single hydrogen environment or flavour, as I call it. These hydrogens here are identical to these hydrogens here, so it's C. 24. Which of the following contains the greatest number of negatively charged ions? If you were with me for hire, I joke about this being a fingers and thumbs type of question, whereby you have to look at the compound here and you have to calculate the number of moles of ions. You've probably got, if you're at a different school, you've probably got your own way of doing this. I don't see a shortcut for this. This is a horrible donkey question where you've just got to slog away at it. So if we work out the moles, first of all, we've got 0.4 times 0.1 for this one, times, and then you've got 1 zinc ion and 2 nitrate ions, so there's a total of 3 ions here. I'm just going to go down and do this for all of them. So again, I'll probably pause the video and so you don't have to watch me raving away like a lunatic. 2 sodium ions and 1 sulfate ion here as well. Let me pause. Okay, there's our numbers. And there's the answer, B. I just went through all of that and I've realised I've used the wrong multiplier. Let me just catch myself. Negatively charged ions, hey? RT, FQ. Read the flipping question, which means it's not the total number of ions, it's only the negative ions. So that becomes a 2. I'm going to pause and remultiply these. And our corrected figures are here, and the answer is in fact A. 25. The covalent bond in a hydrogen molecule can be broken to produce halogen atoms when exposed to light of appropriate energy. The bond enthalpy is the energy required to break 1 mole of bonds. Which halogen would require a minimum of this energy here to break 1 covalent bond? Which halogen would require a minimum of... Oh, right, a mole of bonds is the bond enthalpy. How are you supposed to know? Data book. Let me go and get one. Okay, page 11 of the data book. Now, I've just realised there's something quite sneaky about this, because they're sort of expecting you to manipulate Avogadro's number, which used to be in higher chemistry, in fact. They took it out of higher chemistry. Avogadro went bye-bye. And it's sort of vaguely mentioned in advanced higher, which is fundamentally shocking to me as a chemist, considering it's the number of things per mole. So what you'd have to do is, this is 1 covalent bond, and this is energy per mole. So basically what you're doing is taking 3.22, multiplying it by Avogadro's number, because that will give you the energy to break a mole of bonds. 6.02 times 10 to the 23. 3.22 to the negative 22 times 6.02 to the 23 gives us 194 kilojoules. Now, if we have a look at the bond enthalpies, we come across on page 11 that is, bromine. Bromine matches up to 194. And we have to go back to my cursed question 6, which I'm actually still stuck on, because I have not had any flashes of divine or indeed Dawkins style inspiration. Which of the following represents the enthalpy of formation of a compound? Maybe sodium bromide isn't I'm pretty sure sodium's... Oh, I was about to say, I'm pretty sure sodium bromide is a solid at room temperature. That's a gas, hey? Which means the answer is 6. Right, marking time. Let me mark this and I'll see how I've got on. Thank you for listening, folks. As before, I haven't cheated on this, so that means if I have got any wrong, then I'll be back with you in just 2 seconds. And if I've got them all wrong, if I've got them all right, then thank you for listening. Bye-bye. Okay, that didn't take long to get wrong. Number 3, the number of unpaired electrons in a chromium. Oh, chromium. Oh, that's why they've asked about that. I should have known better. Chromium isn't 4s2, 3d4. It's actually, it's more stable when this is half filled, according to the SQA, although other sources like, excuse me, other sources like ChemWeb say that might not be simply the truth. So 3d5, there are 6 in total there. Doho! Mistake number 2. I didn't read the axes carefully enough. I looked at another classic exam mistake. I looked at this one and assumed that all the axes were rate against concentration. And if you look at these two, you find they're not. This is concentration against time. Now, it cannot be that answer. Now that I know what the axes actually show, then because this would be true, by the way, that would be true for rate against concentration of X. But that's not what we're seeing. Now, concentration of X, if it's a reactant, does not remain constant forever. That's a nice trick. That means you'd never ever use it up. So that means it's actually got to be D.